Let's look at a new concept today in momentum. We know the law of inertia, which states that unless and until an external unbalanced force acts on a system, acts on an object, you cannot change its state of motion. In third law, we also saw that internal forces cause no change in the state of the system. The internal forces tend to cancel each other out. One of the best examples that we can give is trying to push a car while sitting inside the car and pushing against the dashboard, right? And you can immediately see that the forces that are being applied cancel each other out, and it cannot really produce any change in the state of the system. So I present to you a problem. There is a bomb that's going to explode. Its fuse has been lit, right? And when the fire reaches the gunpowder, then there is going to be an explosion. And so when the fire reaches the explosives that is there inside the bomb, then it's going to explode. So a little while later, there is a huge blast. Where shall I show it? I'll show it here on this side. So how do I show a blast? Okay, and the fragments of metal or whatever it is, they are all flying about in all sorts of directions. Actually, if you realize it, it's these things that actually do the harm
Damage.
generally, because they are
Like,
called, they are the
yeah.
shrapnels that actually go and hit people and cause the damage, because otherwise it's just expanding
They're
gases.
like 100 bullets. Yeah.
Yeah, so otherwise most of the rest of it is just expanding gases. So it blew up and all these pieces are flying apart, and obviously now there is a change in the state of motion of the particles that are involved in this blast. So now I ask you the question, if the law of inertia was true, and then the third law, that is internal forces cannot cause change in the state of the system, is true, then how come the particles over here are accelerating and moving, right? What happens to these two statements vis-a-vis this particular situation? Do you see the contradiction, or do you not even see the contradiction? And if you do see the contradiction, how do you explain what is going on? So my basic question in this situation, and I'll sort of talk about a simplified simplified argument of the same situation over here, is all of these particles, are moving out with some velocity. Okay, um, and the thing is, before this, the velocity of this object, what was it? The velocity of the bomb
Zero.
before the blast?
Zero.
0. Okay, so how come from 0 velocity it is producing so many different velocities? You can say this is velocity v1, this is v2, all the way to vn. So many different velocities are there. How did this happen? If internal forces are the only ones that are involved, and internal forces cannot change the state of the system, then how did this happen? And if you are a little confused because the number of particles are high and the number of velocities are high, let us take a theoretical simple system. This may not even be so theoretical. We may actually be able to perform this kind of a thing. Take a box, a tiny explosive placed inside the box, controlled blast, and it so happens that this object breaks up into two particles and moves in opposite direction. So the velocity before the blast is 0,
What is the
but
action?
there is a non-zero velocity after the blast is over. So now my question again is, how come internal forces seem to be changing the state of the system? Or there is no inconsistency over there, the system has actually not changed, or the statements are wrong and we have to start all over again. What do you think is the correct explanation? Yeah, now you wanted to say something, Ishan.
Yeah, are we just assuming that the system has changed its state of motion?
Exactly, we are assuming that because it looks like that. From zero velocity, it has gone to a non-zero velocity in these two cases, and in all of these particles in this case.
But,
So how is that possible?
but V1 and V2 are equal and opposite, right? So they cancel?
Why do you say that V1 and V2 are equal and opposite?
They're not?
Move in two different directions.
Like the length of them seem to say so.
See, you
They
may
are
say,
moving into different.
you may say, yeah, okay. You may say that in this situation, V1 and V2 are equal. So you're saying, okay, because this is V1 going in this direction, this is V2 going in this direction, they look like they are the same. So maybe they are equal, and therefore the combined velocity of these two is still equal to zero. But can you say the same thing over here where there are so many particles that are involved in the blast? Maybe there is a tiny particle which has got a very high velocity. Maybe there is a large particle that has got a little bit lower velocity. In that case, then how do you, will your argument still hold true? Basically, what you're saying is it does not matter. All of the velocity components, V1 plus V2 plus V3, all the way to Vn,
Yeah, sigma f should be 0.
not sigma f, the sum of all the velocities, sigma v in this case.
Yeah.
What makes you say that?
Because like I believe in the third law and I think that no external forces involved here.
Because
And
no external forces are involved, you seem to think that that will be true. Okay, so now let me throw another problem into the mix. Okay,
No, the boat problem is also like that.
sorry,
The boat problem, remember?
board problems.
Boat.
yeah, the boat one, the dog in the boat.
I don't know. I'm not sure what you're saying. So Ishan is saying that, look, since I accept the validity of these two laws, I'm saying that there is no chance that there is going to be a discrepancy. It is obvious to me that V1 and V2 are equal and opposite, and that they are going to cancel each other out when I add them together. And I extrapolate that to this situation also and say that even in this case, all of the velocities should add up to become zeros, because after all, if there is a velocity in this direction, there's something in the opposite direction, there's one here, there must be another going in. So I feel they are all going to add up and become zero. Okay, so now I'm going to throw something else into the mix, and that is this. In this case, the two particles broke up into seemingly equal halves. Okay.
Yeah.
So therefore, the velocity in this direction, the velocity in this direction seems to be the same. Now, let us say that that's not quite what happened, and the velocities, the object broke up in a slightly different way. Most of the object went towards the left, and there was a tinier piece that went towards the right, with obviously a greater velocity in this direction. Now it does not look like V1 plus V2 will be equal to 0, because the V1 in this side has got a greater magnitude, than the V2 on this side. So this cannot be equal to 0. So now what do you say is the situation? For after all, this is quite entirely possible. How do you explain that? Okay, so the story so far is that we are kind of struggling to understand this situation where you say two pieces break up, but one is obviously much smaller than the other. Then the smaller one gets a larger velocity and the bigger one gets a smaller velocity. I hope that is clear why that happens, because the force is the same. So obviously the smaller one will go faster and the bigger one will go slower. And then it says that somewhere it's pointing to you to say that, okay, this one has a mass m1 and this one has a mass m2. Let us look at the momenta, not the velocities. So forget about the velocities for the time being. They don't seem to make a lot of sense. But let's look at the momentum. Can we now say that the momentum of m1, which is m1 v1, okay, plus the momentum of the other one, m2 v2, okay, can that be equal to 0? That seems to make some sense. Why?
Yeah.
Because the initial momentum was mv, which is equal to 0. That is the total mass of the object multiplied by its velocity, which is 0. So that was 0, right? And this is after the blast. You're saying small m1, big v1, big m2, small v2. And of course, if v1 is positive in this direction, then v2 is negative in the opposite direction. So when you factor all that in, it seems there is a possibility that this can become 0. So here it's good because we are saying, look, what is happening is the velocities are changing, the masses are breaking up, the gases are expanding, forces are acting. These things might kill people, but fundamentally, the momentum which was there before and the momentum which was there afterwards are exactly the same. Okay? Or in other words, momentum is conserved. Okay, and then what Ishan saying, why do you say momentum is conserved, is because we are saying that, look, momentum can change only if there are external forces, and all of these forces are internal forces. They are big internal forces, but they are internal forces. So eventually there is no F, there is no external force. So therefore delta mv is not possible. If ft is 0, then delta mv is also 0. So there is going to be no change in momentum in either of these systems. So coming to this system also, you need to say, okay, there is m1 here, there is m2 here, there is m3 here, there is m4 here. This is mn. And all we are saying is that sum total of all mv is still going to be equal to 0. Why do we say that? Because there are no external forces involved. So therefore, there cannot be any increase in the momentum of the entire system. I think that kind of makes sense, but you people tell me, does it make sense to you or not?